Okay, the next method we call, this is the method of finding yp, we call variation of parameters. With this method, we are going to assume yp from yc. So that means we still need to use yc for this method. Another advantage of this method over the UC method and operator method is just that the fx here, the function here, is not need to be UC function, could be any function. So what if we have the differential equation as the second order differential equation? In order to find yp by this method, we have to find yc first. So that means if this is our differential equation, we just set it equal to 0 and then find yc. In here, in your yc, you would have y1 and y2. Right? Your yc combined with y1 and y2. So with this method, we are going to assume yp. Yp is equal to v1 y1 plus v2 y2. y1 and y2, we find it from our homogeneous differential equation, which is that we set our differential equation to be equal to 0 to find yc. So that we would get y1 and y2. For yp, we have to find v1 and v2. v1 and v2 got to be a function of x. Or it can be a constant. It depends. Okay, it can be constant or it can be function of x. So the way to find v1 and v2, y1, y2, you know. If we can find v1 and v2, so we know the answer yp. And the way to find v1, they're saying that we just plug the value of yp into differential equation. So our differential equation is the second derivative. So we got to do the first derivative of yp and second derivative of yp. Now the first derivative of yp, since v1 and y1, both of them are a function of x. So when you do derivative, you got to do the product of the function, the derivative of the product of the function. So I would get v1 times the first derivative of y1 plus y1 times the first derivative of v1. Do the same v2 and y2. The first derivative of this would be equal to v2 times the first derivative of y2 and plus y2 times the first derivative of v2. With this method, it's saying that we don't want the second derivative of v1 and v2. So if you do the second derivative of yp, you would get the second derivative of y1 and y2. v1 and v2, but we don't want that. If we don't want it, the things that we got to do in order to get rid of the term of second derivative of v1 and v2, we have to put another assumption. This term and this term are the terms that lead us to second derivative of v1 and v2. So we're saying that if we don't want it, the things that we can do is just that have these two terms equal to 0. So that means you would get y1 times the first derivative of v1 plus y2 times the first derivative of v2 equal to 0. That is the assumption. That is our assumption by this method. From doing this, our first derivative of yp would change to be this, right? Because these two terms You plus them together and then they equal to 0. So now your equation 3 just reduce to this form. And then what do we do next? We do the second derivative of yt. Again, both of these functions are function of x. So when you do derivative of it, you got to do the derivative of product of the function. So you would get equation 6. Then you replace equation 2, equation 5, and equation 6 into your differential equation. By doing that, we would get equation 7 there. From equation 7, if you take a look at the term that I circle with the red color, this term, and this term, we would get a0 times the second derivative of y1 plus a1 times the first derivative of y1 plus a2 times y1, and the whole term times v1. The term in parentheses is equal to 0, right? Because your y1 is the answer of your homogeneous differential equation. So it's equal to 0. There. See? The term in parentheses equal to 0, right? Because your y1 is the answer of your homogeneous differential equation. And your homogeneous differential equation is saying that a0 times the second derivative of y plus a1 times the first derivative of y plus a2y equals to 0. So if you plug the value of y1 in there, it should be equal to 0. If you plug the value of y2 in there, you would get 0, right? We proved it already. So the red circle, you would get this one. The green circle, you would get this one. Okay? This one also is equal to 0 too, because y2 is the answer of your homogeneous differential equation. Now, after you plug equation 2, 5, and 6 in there, you would end up with very simple one, which is this equation. You have a0 there, you just move a0 to divide fx. So you would get equation 9. Now we have two equations, which is equation 4, which is our assumption, and equation 9, which is coming from the value that we plug into the equation. So from these two equations, we have only two parameters which is unknown. Those two parameters are the first derivative of v1 and the first derivative of v2. So if this is two equations with two unknowns, you should be able to find the value of those two unknowns, right? So if we can find the first derivative of v1, then we can find v1. Likewise, if we can find the first derivative of v2, we can find v2. So the simplest method that we can use to find the first derivative of v1 and the first derivative of v2 with these two equations, we call Cramer's rule. This is a briefly introduction to you what is Cramer's rule. It is in the metric, right? It is in the metric subject. If we have two equations like this, a0, b0, c0, is a constant. A1, B1, C1 is a constant. So you have x and y. You have two unknowns, which is x and y, and two equations. The way to find x, you can write it down in the term of matrix. The way to find x is say that, for Kramer rule said that you just replace the coefficient of x by the coefficient of c. There. And then you find the determinant of that, divided by the determinant of coefficients of x and y. If you want to find y, you place the constant C0 and C1 to the coefficients of y. So if you want to find y, you put C0 and C1 to the coefficients of y. You find determinants of it, dividing by the determinants of the coefficients of x and y. Now, if you take a look at our equation, from that, if you want to find the first derivative of y1, then you just do exactly the same, because y1 and y2, the first derivative of y1 and the first derivative of y2, you know those functions, right? Because y1 and y2, you get it from yc. The only two unknowns are the first derivative of v1 and the first derivative of v2. So from this, with Kramer rule, you can find the first derivative of v1 and the first derivative of v2. Now, if you want to find v1, can you do that? Yes, because you know that the definition of the first derivative of v1 is equal to dv1 by dx. Because you know this function, you can find v1 by integral. v2, exactly the same as v1. You know that the first derivative of v2 is equal to dv2 by dx. If you want to find v2, you just do integration of the first derivative of v2 by dx. When you know v1 and v2, you just plug v1 and v2 back into your assumption of yp. Then you get the answer. The method itself is quite complicated, but the thing is that it's good whenever you don't have to use the function as your function fx in the differential equation.